Hello again, everyone. Thanks for checking in yet again for interesting video. I don't know if it's interesting. If you're interested in this stuff, it is. Otherwise, I don't know. The topic of this clip is the nature of light and how it relates to the nature of the atom, especially the hydrogen atom, and how we first started to discover and investigate the structure within an atom itself. So we call light a specific kind of electromagnetic radiation. We'll talk more about these in a little bit. No, probably in a future video. Yeah, right. Next video. So this seems more like a physics topic, but we need to address it in order to fully understand the nature of the atom and its interaction with electromagnetic radiation, and therefore how we first discern what's inside of an atom, what's going on inside the atom. Excuse me. Imagine over here we have some kind of a changing electric and or magnetic field, like perhaps an oscillating electron or an accelerating electron. And that negative charge moving in space and time creates a electric field that oscillates, kind of like a sine wave, and a magnetic field that also oscillates in a similar pattern in a perpendicular direction to that. It's kind of hard to imagine the blue one's in the blue plane, that's the forward and backward plane, and the red one's in the up and down plane. But that's the oscillation, but the direction of travel, propagation of that wave is in this direction, from left to right. And it travels at an unimaginably large rate of speed, almost 300 million meters per second. It's crazy fast. We'll deal with that in a minute. A couple of properties, characteristics of waves. The distance between a crest and a crest, or a trough and a trough, or two successive points, say between here and here, is called the wavelength. In some cases, with EM waves, electromagnetic waves, you can actually imagine the distance because it's measurable, like a meter or 2 meters. Well, not directly measurable, but I shouldn't say that, because even the smallest waves are measurable. But the wavelength is also associated with something we call frequency. Frequency is the number of waves being counted per second, or being generated per second, or passing a particular point in a second. So if this wave's moving from left to right, the wave train left to right, we're counting the number of waves that pass, say, a given point in 1 second. It's called waves per second, or hertz, or 1/seconds. The tallness of the wave is called the amplitude, which is mostly associated with its brightness. Bright light has a tall amplitude, and dim light has a lower amplitude. By the way, the wavelength and frequency do determine the color of the wave. Well, I say color in quotes because it might not be a light wave. It might be a radio wave or an X-ray of some kind. Here's the red light with a longer wavelength, and yellow light has a shorter wavelength, and blue and purple have even a shorter wavelength. Turns out the shorter wavelengths have higher frequencies, and higher frequencies have higher energies. Oh yeah, dim light, bright light. Shallow, very deep and tall. Here's a summary I wrote up of the EM spectrum, although there are much better versions of this, much prettier. But I wrote the radio waves and TV waves have the longest wavelength and the lowest frequency, and also the lowest energy, followed by infrared, and then red, orange, yellow, green, blue, violet are part of the spectrum we know and love in rainbows. But this is only this is not to scale. This is a very small sliver of the overall spectrum. I'll show you a better one in a second. But red has very long wavelength and low energy, very relatively. And relative to that, violet has a higher frequency, a higher energy, and a smaller wavelength. Beyond violet is ultraviolet. Beyond that's X-rays, and beyond that, gamma rays. As you probably know, X-rays and gamma rays are so high in energy they're damaging to tissue. So you have to watch out about how many X-rays and or gamma rays you encounter in your lifetime. Hey, there's a connection between frequency and wavelength and speed of the wave, and here it is. The speed of the wave, doesn't matter if it's light, radio waves, X-rays, they all travel and follow the same principles of the speed of propagation is equal to the frequency times the wavelength. This is in waves per second, or hertz, or 1/seconds, and this is in meters. So this would be meters per second. That's a crazy idea how it works like this. speed of the EM wave, perhaps light, perhaps some other variety of, perhaps in some other category of the spectrum, is the frequency times the wavelength, and the units again are like this: meters per second for the speed, the wavelength is in meters, and the waves per second, or 1/seconds, or hertz, is the unit of the frequency. Example, what's the wavelength of red light of this frequency? My goodness, that's a lot of waves coming by per second. So I put that on the bottom, and I put the speed of light on top, so that this one times this one would give you this one, and just do the math and do the scientific notation correctly. It's right. Oh yeah. Oftentimes the wavelength of visible light's mentioned in nanometers. So red light this red light has a wavelength of about 649 nanometers. The human eyeball is not sensitive to anything longer than that, like in the infrared. What's the wavelength of a radio signal with a frequency of 100.7 megahertz? Oh yeah, I think this would be on the FM dial. Yeah, megahertz, kilohertz. You can tell how old I am because I actually listened to the radio when I was young. And on the dial they had these KHZ and MHZ labels. Indeed, it's true. Maybe you know what I'm talking about. And anyway, the frequency into the speed of light gives you the meters. Oh my gosh, that's about 3 meters. So this wavelength, the wavelength of an FM radio wave is about 3 meters, or 2 meters, or 1 meter. Depends on the frequency, right? Here's a white light incident upon a spectrum coming up from here. So the white light comes into the spectrum like this, and then the spectrum. The white light comes into the prism, or a droplet of water acting as a prism, and it's refracted into the colors of the rainbow. Part of the reason is because of different wavelengths. The shorter wavelengths are bent more, and the longer wavelengths are bent less. Evidence that white light's made of different colors. I swear this girl looks like a robot or something. I don't know why. Perfect skin. White light comes into her shirt, bounces off her shirt, but only one color of light is reflected by her shirt, and you know it's red. The other colors are absorbed by the shirt. So it's kind of interesting that transmitted light versus reflected light, it's a little bit opposite. No, not necessarily opposite. If I had a red container of red Kool-Aid here, the white light would come into the red Kool-Aid, and the red Kool-Aid would absorb everything except for red, and it would transmit red. Similar story here, the red shirt, the white light comes into the shirt, and all the colors are absorbed except for the red. Here's another version of the spectrum, going from long wavelength, low frequency, to high frequency, high energy, and low wavelength. Continuous spectrum again. We call this the spectrum of white light, and it makes sense if you've ever seen it. If you've ever seen it, taken white light and looked through a prism, broken it apart into the colors. We see all the continuous spectrum, but if we take a gas, like a specific element, and excite it with electricity, or if we don't want to excite it with electricity, we excite it in a fire, and we get sodium, potassium, lithium, the elements, the atoms of those elements, it even works with salts of those elements, excited in the fire, they give off their particular, any one of a number of particular wavelengths and frequencies. So this is not white light, not white, not white, not white light. They give off particular colors, only particular colors. So the first one understood is hydrogen, and the hydrogen atom looks like this with 1, 2, 3, 4. I call this the finger 1, 2, 3, 4. Hard to see that one over there. I call this a particular fingerprint of color for emissions of hydrogen. I wonder why hydrogen doesn't give off other colors. Why not something in between there? Well, they figured it out, believe it or not. And let me tell you more of the story. Oh, by the way, helium is different, barium is different. So every single element, oxygen is different, neon is different. Every single element has a different fingerprint, I call it, of emission. And not only that, whatever the excited gas, excited element emits, the non-excited gas, or just a cool gas, would also absorb that same frequency. So there's something about these thin slivers of frequency that are either given off or taken in by that same atom. Particularly, let's keep it simple with hydrogen. It only has one atom. and I'm sorry, only has one electron. So in that sense, is perhaps the easiest to understand. And this is hard to believe. Unlike the solar system, where the planets could orbit in any distance from the sun they want to, or it's just coincidence, the Earth is at this present location. Well, that's what a scientist would say, right? The atom is not that way. If this is the nucleus, there's level 1, level 2, level 3, level 4, level 5. Particular levels, spheres, for now, spheres around the nucleus where these electrons can exist. They can stably occupy these territories, but they cannot hang out here, and they cannot hang out here, and they cannot hang out here, but they can hang out here, and they can hang out here. And transitioning from one to another, called a quantum leap, either gives off light. If the electron falls to a lower level, it's giving off light. But if the electron jumps up from, say, level 2 to level 4, it would need to absorb this particular color and frequency of a photon. Oops, there's a new word, photon. It's a little chunk. It's the smallest possible chunk of light. Yeah. And all right. So this transition from a 5 to a 2, high energy to low energy. So once the electron gets here, it has less energy. Once it was up here, it had more energy. And it's hard to believe that energy is actually calculable. So for the purple transition, here's the equation. Well, here's the equation. The energy is equal to h nu or hc over lambda if I substitute for frequency in the c over lambda. And then I can do a little calculation. H is called Planck's constant. It's just a special number that we discovered. It helps describe some of these numerical values. Planck's constant times the speed of light divided by the wavelength gives me a number of joules of energy. Interesting. That's a small number of joules, but it's only for one photon, one little packet of light energy. Here's the green one. The only thing that's changed is this denominator, and so that changes a little bit too. Notice the green light has a little bit less energy than the purple light. And the red one. This is all based on this one, the green, the purple, the red. The red one, the denominator changes again, different wavelength, a longer wavelength, so that makes the energy less. And so the numbers are right here. And voila, lo and behold, purple has more energy in joules, and green has less energy, and red has even less energy. Here's an example. I'm talking about photons of particular colors. If I had a 532 nanometer wavelength light, what would be the frequency for that? Let's see. Oh yeah, it's a little calculation. 5.4 times 10 to the 14 waves per second. That's a lot of waves per second. And so the energy for one photon would be E equals h nu, or in general it's E times n times h nu. N is the number of photons. So if I had, say 11, just a random number. Hard to imagine counting 11 individual photons. They're so small and so elusive. But if I did, I would take that frequency times Planck's constant times the number of photons. Or how many photons of this light would it take to deliver a certain amount of energy? So if I wanted 0.075 millijoules of energy, then that would be how many photons, Planck's constant, times that same frequency. And the frequency determines the energy. So the number of photons, but in one photon, this times this. Interesting. So look at all the photons it would take to acquire even a small amount of joules. Here's another interesting little schematic. We actually have an equation to estimate these energy levels for the electrons in the hydrogen atom. First level, second level, third level, fourth level. The further you go, the closer these levels get to each other. So layer 5 would be, layer 6 would be, layer 7, 8, 9, 10, 11. They start stacking closer and closer. It's called the fine structure constant. And level 1, level 2, level 3. I don't think we'll actually have you do these calculations on the exam, so don't sweat it. But interesting how we have lower energies and higher energies. To leap up would have to absorb a photon. So to go from here to here, I got to absorb one photon. But the electron wouldn't stay excited for long. It would jump right back down and emit that same frequency photon. And same story here. Going down would give off a photon, but how did it get up in there in the first place? It would have to be excited with electricity or fire for that electron to get up in the first place, get up to a higher level. And when it comes back down, it gives off that same frequency. And these are so well known that they're actually given terms for transitions to level 1, from transitions to level 2, transitions to level 3. Guys, I am out of time, so thanks for watching, and I'll see you in class.